All right, let's continue on with our exploration of trig integrals, this time looking at integrals that include just tangent, powers of tangent, and powers of secant. Okay, we're going to look first at the case. So unlike the symmetry of cosine and sine, tangent and secant aren't quite the same, right? Their derivatives don't mimic each other like they do the sine and cosine. So in the case where let's remember also the identities that we will use perhaps in this case. Remember the Pythagorean identity, tangent squared x plus 1 equals secant squared. So we know what secant squared is, or we could have secant squared x minus tangent squared x equals 1, or we can solve for tangent squared. So tangent squared x equals secant squared x minus 1. So if we end up replacing tangents with secants, they look like that. If we end up replacing secants with tangents, they look like that. Also remember the derivatives are different, right? So the derivative of tangent is secant squared, and the derivative of secant is secant x tan x. So they are not symmetric like the sine and cosine are. All right, so in the case where n is even, and n is the power on secant, we are going to reserve one of the secant squareds. And note that if we take secant squared off, we still have even powers of secant left. Okay, so we will convert those, if there are any left, convert remaining secants to tangents using the Pythagorean identity right there. And then we do a u sub on tangent. Okay? That is if your power on secant is even. So let's look at an example. Let's say we have, and it doesn't matter the power on tangent. So let's say we have tangent to the 5th x secant squared x dx. Okay, so I'm going to reserve one power of secant, which, actually, let me just change this so that it doesn't seem like there isn't anything left over. So let's make it secant to the 4th. Okay, we're going to pull off one of our secant squareds. So we end up with tangent to the 5th x, secant squared x, and then we pulled off one secant squared right there. We will convert this to tangent using the Pythagorean identity. So then this becomes tangent to the 5th x. And then remember, it's not the same Pythagorean identity as sine and cosine. Secant squared is tangent squared plus 1. So this becomes tangent squared x plus 1, and then we still have the secant squared x reserved. And now we do a u sub on tangent. So if u is tangent x, then du is secant squared x dx, which we reserved for this very reason. So now we just replace all of these. That's u to the 5th, u squared plus 1, du, and now it's just a bunch of power rules. That's really u to the 7th, right? So that's u to the 8th over 8, plus that's u to the 5th, so u to the 6th over 6, plus c. And just like before, we always go back to our original variable, which was x, and our u was tangent x. So this is tangent to the 8x over 8, plus tangent to the 6x over 6, plus c. Okay, so that's what we do when we have an even power on secant. Well, and it doesn't matter the power on tangent. If we have an odd power of tangent, then this time we're going to reserve a secant and a tangent. Okay? Because then we're going to do a u sub on secant, in which case we need to have a secant x tan x for the du. Let's see it in action. So let's write down what I said. In the case where your power on your tangent is odd, we are going to reserve, reserve a tangent x, secant x. Now, of course, this does, you do need to have some secants, so we might need to consider that the case where there are no secants, like say we just have tangent x or we just have tangent cubed x. Because how can we reserve a tangent and a secant if we don't have one? So this is assuming that we should even put that n is greater than or equal to 1. So we do have to have a secant. Actually, we probably need, we need to have at least one secant. Okay, then we will convert the remaining tangents, because we've pulled off one tangent and a secant, so we will now have even tangents left. We'll convert the remaining tangents to secants using the Pythagorean identity. And then we'll do a u sub on secant. Okay, so let's look at an example. So maybe we have tangent cubed x secant x dx, okay? So I have m is odd, and I have at least one power of secant, which is what I need. So I'm going to reserve one tangent secant x. So I now have tangent squared x and then a tangent x secant x dx. That's reserved. I'm going to convert the tangent squared to secant squared using the Pythagorean identity, but this time it's secant squared minus 1. So this becomes secant squared x minus 1, right, times tangent x, secant x dx. And now we do a u sub on secant. Du then is secant x tan x, so we needed to know that, dx, which is right there. So then this integral is just u squared minus 1 du. And it's just a straight up power rule, right? U cubed over 3 minus u plus c. Replace your u back with the original variable. Secant cubed x over 3 minus secant x plus c. Now those are the two main cases. If both n is odd and m is even, then we might need to be creative. So I realize that's not a straightforward answer, but it's not a clear-cut answer in this case. But I do want us to make sure we know how to find the cases like, what if it's just this, right? So tangent x is odd, but and the power on secant is 0, which is even. So how are we going to do that, right? And you did do this back probably when you did u subs in Calc 1, but let's just go ahead and do this one to make sure that we are on the same page. So you could convert this to sine x over cosine x, right? And then do a u sub on cosine. So then, cosine. Let's be clear. So u is cosine x, then du is negative sine x dx, which I have basically there, except I'm missing a negative, so I insert it, take it out. So now I have the negative of 1 over u du, which we do know to be negative natural log of the absolute value of u plus c. We always go back and we write this as the negative natural log of the absolute value of cosine of x. And that is a fine answer, but that's generally not what you'll find in tables of integrals. So if you put that negative up here, so it becomes the natural log of cosine of x to the minus 1, that's 1 over cosine, or secant. So natural log of secant of x plus c is really the one that you'll see in books and tables of integrals. Okay, another one that you should know, here we'll come over here and do it, and it's one that's not as intuitive to solve, so we'll do it here together, and that is the integral for secant alone, okay? And we're going to do some creative maneuvering here because it's not an easy one to show. All right? So I'm going to do a trick that lots of mathematicians do in proving things. They insert creative ones, right? So I could rewrite this as secant x, and then I'm going to insert this 1 here. Secant x plus tan x over secant x plus tan x dx. So that's really just inserting a times 1, right? There's nothing wrong with that. If I distribute this numerator, I end up with secant squared x plus secant x tan x all over secant x plus tangent x dx. Now, hopefully, if you're looking at the numerator now, that numerator, let me rewrite this denominator. Okay, I'm going to rewrite it this way. Tangent x plus secant x. All right, do you see that the numerator is really the derivative of the denominator, right? The derivative of tangent is secant squared, the derivative of secant is secant x tan x. So I feel like I see a natural u sub now. If I let u be tangent x plus secant x, that writing is kind of being wonky, then du is secant squared x plus secant x tan x, right? So then my integral becomes 1 over u du, or the natural log of the absolute value of u, which is this. So that's one I would somehow commit to memory. Okay, so let me come up here and write it. The integral of secant x dx is the natural log of tangent x plus secant x plus c. That one's going to be harder for you all to derive on your own because of this creative maneuvering, whereas I do think you could recreate tangent x on your own by a simple u sub. Okay?